When we take a look at the properties of limits, so suppose the limit as x approaches a of f of x and the limit as x approaches a of g of x both exist and c is a constant, then the following properties have to be true. The limit as x approaches a of f of x plus g of x would have to be the same as the limit as x approaches a of f of x combined with the limit as x approaches a of g of x. They're just a sum. The limit as x approaches a of f of x minus g of x has to be the same as the difference between the two limits. The limit as x approaches a of f of x minus the limit as x approaches a of g of x. This difference still has to be the same. For the constant, the limit as x approaches a of c times f of x would have to be if I just took c and multiplied it by the limit as x approaches a of f of x, remembering that c is constant in this case. If I'm looking at the products, the limit as x approaches a of f of x times g of x has to be the same as if I took the two limits and multiplied them together. The quotients would have to exist in the same way. The limit as x approaches a of the two functions divided by each other has to be the same as the limit of one function divided by the limit of the other function, remembering that the limit as x approaches a of g of x cannot equal 0. If that is a non-permissible value, this obviously doesn't work. I can use it with the positive exponent using the power rule. The limit as x approaches a of f of x to the power of n, as long as n is a positive integer, has to be the same as the limit as x approaches a to the power of f of x, and then take that and put it to the power of n. And because this works for the powers, the same also has to be true of the roots. The root of the radical has to be the same as the root of the limit. So, starting with the basic limits, the limit as x approaches a of x has to equal a. So if I just had a value, say that x was approaching 5, the limit as x approaches 5 of just x has to actually equal what x is. If this is 5, then that has to be 5. The limit as x approaches a of a constant is just going to be that same constant. So if I said that the limit as x approaches 2 was the constant 5, then that has to be the same as just that constant of 5. When we use properties 6 and 7 using the power rules and the root rules, I can say that the limit as x approaches a of x to the power of n is going to be the same as a to the power of n, because remember that x would be the same as the a. The same thing would be true if I took the limit as x approaches a of the nth root of x. It's going to be the same as the nth root of a, as long as it actually exists, because remember, once again, in this case, the x and the a are going to be the same. So let's apply this using example 3. First, we're going to use method 1, the property of limits. So if I said the limit as x approaches 1 of x to the 4 minus 5x squared plus 1 divided by x plus 2. Because we're using it using the quotient rules, if I'm doing one divided by the other, it has to be the same as the two limits divided by each other, which means that I would say that the limit as x approaches 1 of x to the 4 minus 5x squared plus 1 divided by the limit of the second one, or the denominator, the limit as x approaches 1 of just x plus 2. Then from here, I can use the sum and the difference rules. Remember that I'm just taking x to the 4 minus x to or 5x squared plus 1 and x plus 2. So I'm going to split this up and say that this is equivalent to the limit as x approaches 1 of the first term, x to the 4, minus the limit as x approaches 1 of the second term, 5x squared, plus the limit as x approaches 1 of the constant 1. In the denominator, we have that sum again, so I'm going to say the limit as x approaches 1 of the first term, x, combined with the limit as x approaches 1 of the constant 2. Then I can use the exponent rules, or the power rules, if you will, and state that the limit as x approaches 1 of x to the power of 4 minus 5, that constant coefficient, times the limit as x approaches 1 of x to the power of 2 plus the limit as x approaches 1 of the constant, which remember is still always just going to equal the constant. And we're dividing that by the limit as x approaches 1 of x plus the limit as x approaches 1 of 2, which once again is still just going to equal the constant. And now that we're taking the limit of x for all of these, I'm just going to replace that with the a value of 1. So I'm replacing the constants with the constant. And I'm replacing the x's with the a value of 1. And after I do all that, I'm going to wind up with 1 to the 4 minus 5 times 1 squared plus a constant of 1 divided by 1 plus a constant of 2. 1 to the 4 minus 5 times 1 squared plus 1 is negative 3, and 1 plus 2 is 3, and all this equals negative 1, and there's my answer. We can also do this using direct substitution. So, if I'm doing it using direct substitution, if I have the limit as x approaches 1 of x to the 4 minus 5x squared plus 1, all divided by x plus 2. All I have to do is check and make sure that when I substitute in the value for x, it is not indeterminate. If I'm dividing by 0, it's not going to work. But in this case, if I replace the denominator with 1 for x, then I don't wind up with a denominator of 0, which means that now I can just directly substitute the a value in for all the x's, and it's just going to give me 1 to the power of 4 minus 5 times 1 squared plus 1, all divided by 1 plus 2, which we already know is negative 3 over 3, or negative 1. For obvious reasons, the direct substitution is significantly simpler if you can do it. For example 4, it wants us to evaluate the limit as x approaches 3 of the square root of x squared plus x. If I'm using my properties of limits, then I'm going to say that this would be the same as the square root of the limit as x approaches 3 of x squared plus x. Now, because I have a sum, I can use my rules for sums and say that this is the square root of the limit as x approaches 3 of x squared combined with the limit as x approaches 3 of x. I can use my power rule for the first one. The square root of the limit as x approaches 3 of x squared, and combined with the limit as x approaches 3 of x. Now that we're taking the limit as x approaches a value of x in both cases, I can just substitute the limit of that for what x is approaching. And I'm going to get the square root of, replace the limit with 3 squared plus replace the limit with 3. This is going to give me the square root of 3 squared plus 3 is going to be 12, which is the same as 2 root 3. If I'm doing this using direct substitution, then I would just say that if I'm taking the limit as x approaches 3 of the square root of x squared plus x, then that is equal to the square root of 3 squared plus 3, which is equal to the square root of 12, which is equal to 2 root 3, and I get the exact same answer. We can see that direct substitution provides us with an answer in the above example. Functions with this property, the limit as x approaches a of f of x is equal to f of a, are called continuous at a, which means that the function would not have a point of discontinuity where this limit occurs.